Introduction and inviting me to present my research. So hope I'm audible well. So today I'm going to present um, our work that is done in the last few years on designing efficient AI models by a method called pruning. So before moving further, just want to introduce a bit more about my team. So I work with the AI for Sound project with Professor Mark D. Plumley and other colleagues from design research and software engineer, along with some PhD students, where we try to explore sound and AI application to improve the productivity at home and workplace, and also designing AI sound tools for broadcast creative content like for BBC or ND. So today, with this efficient AI models presentation, so I will start with the background on AI models, applications, and then we'll share why we need the efficient AI models and the method to make AI models efficient. So if we see in our surrounding, there exists abundance of information. We can hear, we can see many activities happening in the surrounding, and with our intelligence or brain, we can take decisions, appropriate decisions as well. So inspired from this brain intelligence, there is artificial intelligence, which can also make sense of surrounding, particularly AI, artificial intelligence with deep learning. And it has found application in diverse areas, from security, in healthcare, in environment, in AI for clean energy, or many applications. So basically AI for sustainability has been explored quite well. And the backbone, so a few of the state-of-the-art AI systems that are used in real time. I will share those with some demos. So one of them is the audio classification framework, where audio tagging system can recognize activity in the surrounding using sound. So given AI model, it takes a microphone signal, which is the sound, and tell which activity is happening in the surrounding. So let's see this video, how AI model can detect things in real time.
Murdered. Mr. Harrison's daughter is missing.
So you see, this AI models can cover a wide range of audio activities or any activities in the surrounding. And similarly in image classification, where AI system, deep learning system, has written the error which is given by a human. So they perform really state of the art. And also ChatGPT, large language models, or in robotics with audio visual, this informatics and machine learning things, AI has really revolutionized many areas, and even with in the protein universe, to reveal their structure, and in gaming, where deep learning system AlphaGo has beaten the human experts. So AI is actually everywhere with their deep learning support, and the learning learning resources to build such AI systems powerful. And the backbone of such AI system basically consists of the way AI system learns, which is the deep learning, and the architectures, which is really powerful. And basically the architecture consists of a set of layers, which are convolution layers, pooling layers, and these layers have a set of parameters or transformation parameters, which are learned in an iterative manner by showing a set of examples and optimizing the error between predictions and the true categories. And the powerful nature of this AI is the weights and filters, which are learned through an optimization process. And typically these filters, which are learned in an iterative manner, they use an operation which is called convolution operation, and to produce the output at the next layer. And this operation is multiply and accumulate operation, where the learned parameters, they do convolve local patches in the input, and they produce next layer feature maps. As there exist a number of feature maps in convolution layers, or in overall in deep learning architectures. And let me show you how this intermediate layers within the neural network looks like. So given the input, here. So this is how the feature maps, which are the transformation from filters, they look like. And ultimately the input data, which can be assumed in high dimensional space, is mapped to a vector space where the signal is very sparse, and the categories are the interesting categories where we are interested in classifying or in regression tasks. So with this deep learning system, with the learning paradigm, so AI systems are really powerful, and they can store information in filters and these feature maps. So far AI deep learning seems really great, as we are happy with how it performs in various applications. But it's important to ask or see other side of AI as well. So ask right questions, whether is AI deep learning is doing really great, or are we missing something. So the something that we are missing, I'm gonna talk in next few present slides. So that's the other side of AI. So let's see why AI doesn't seem so great, although it performs state of the art. So if we see or explore other side of AI over time, how AI models evolved, or why they perform state of the art. So typically the large size AI models or over parameterization within AI architectures, it is helping to achieve state of the art performance. For example, for image classification, as you increase the number of parameters and the computations, so you will see the state of the art models. And it's true for other tasks as well. For example, in audio tagging or with GPT models with billions of parameters, you can achieve state of the art performance. And with this deep learning AlphaGo system, gaming system, it requires 2000 CPUs and these many 300 around GPUs to beat the human experts. So this is where the other side of AI is important to discuss, because this is making AI systems resource hungry. And because of large requirement of parameters and computations, these AI models, they are not energy efficient. For example, in the last keynote by Professor Simon yesterday, so he mentioned that memory is very expensive. So because data is required to move from your memory for processing to GPU or to CPU, so it takes this much energy, which is the maximally energy consumed by any other operations. So this is where this AI models become memory inefficient. And not only from the memory perspective, but if you see the environmental impact of AI models, that is also huge. So just an example, so this Google AlphaGo Zero, this gaming system, if it trains for 40 days, so it can cause this carbon footprints, which are consumed by 23 American homes, or is equivalent to 1,000 hours of air travel. And a very simple example that we do at our lab, so with NVIDIA, this GPU, so if it runs for 48 hours, it can generate CO2, which is equivalent to driving an average car for 13 miles. So this is where the other side of AI is really crucial to discuss, and it makes life a bit sad. And when particularly we look to deploy this large-scale AI models on edge devices, because building edge devices is crucial from the privacy point of view, as Eric mentioned in the last keynote lecture. So edge devices provide privacy and local computation and personalization. So with edge devices, it's really a trade-off is that they have limited resources. And when we deploy large-scale AI models on such devices, either we have heating issues or we have inference latency issues. So to test that, we within CVSSP we develop a standalone device with Raspberry Pi for audio tagging. So let me show you this device, how it works first. So this standalone device can send sounds and can send you email notification. But the problem with this device is that if you run this device for 10 minutes and analyze the temperature and latency, so you see that there's a within 10 minutes there's a temperature rise of around 15 degrees Celsius, and the latency also increases. So which means the things are becoming slower as we use devices for longer time, and this is really bad from the user experience side. So to overcome, and also for mobile AI or tiny AI, where the resource constraint of such devices with memory upper limit and storage of weights upper limit. So it's really difficult to compile or to run these large scale AI models. So this is where to address these roadblocks of AI models in terms of memory and computation, and it's important to make AI model efficient. And one of the methods that is used to make inefficient AI to efficient AI is the compression method, where from the algorithm perspective or architecture perspective, we can contribute to reduce the computation and the emission of the carbon equivalent. So this is where I work on making some contribution towards sustainable AI to make this AI more efficient in terms of algorithm or architecture perspective. And this compression is also important to fill the gap between the production and demand, because model size is increasing tremendously, but the production based on the Moore's law so is limited. So to fill the gap to match the production limitations, so we can compress the model to use the suitable hardware for using the large scale models. So this is where compression came into picture. And one other method in AI compression method is the pruning, so that I have been exploring since past few months. So what pruning does is it takes a big deep learning model which has set of parameters and computations, and it reduces its parameters, which means it can reduce the memory required by AI models, and also reduce the computations, which are the multiply accumulate operations to generate feature maps at different layers within the deep learning architecture. So this also leads to make inference faster, right? And this pruning is inspired from our brain architecture, how within our brain neurons and their connections within neurons grows at certain age, and then they degrow or reduce with time. But interestingly, the capabilities of brain remains intact, or we have more capabilities as we grow. So this is some motivation to make a dense neural network to sparse, which means that we can take this analogy to make algorithms or architectures more sparse, and at the same time we can reduce the computation while maintaining its performance, right? Also, if we see the pruning thing, that is inspired from existence of redundancy within AI models. So for this, we analyze it empirically by using a set of examples from different classes and taking one of the deep neural network, where we find that 73% of the filters or the feature maps generated across different classes, they are giving similar information. So which means that they are not discriminative, so we can remove them and still regain the performance or have same performance and reduce the computation complexity. So how pruning is performed is, so let's say we have a architecture with a set of convolution layers. So here I showed one convolution layer which takes a set of feature maps and produces output feature maps. So within pruning, what happens is, so from the set of filters, we aim to eliminate few filters. Let's say if we remove filter 2 out of filter 5, then we can save this parameter storage from this filter, and also the computation which are required by this filter to generate the feature maps in the next layer, right? So ultimately we have saved the feature map storage and its computation in computing this feature map. So this is where pruning at high level can remove the computations and memory requirement. And so now the question here is, out of these filters, which filter to prune or which filter to retain? So for this, there exist filter importance criteria where people do research from different set of methods. So existing literature have explored the active methods, which uses data set to identify which filter to retain or prune. And typically the active methods, they use performance based metrics. For example, they measure the sensitivity of each filter to the performance, and find those filters as unimportant which have more sensitive, less sensitivity to the performance. And other methods, for example, they involve extra parameters to the filter itself, and during the optimization process these parameters are optimized, and the parameters with the low values, they are eliminated along with the filters, right? And other than that, performance based, they are feature map based methods, where given a data set, one can generate a set of feature maps and apply statistics on feature maps generated from different classes, and or explore the geometry of the feature maps, and have similarity measures to identify which feature map or filter is actually redundant, right? So these methods, active methods, since they involve data sets, so they are computationally more expensive and they demand more resources. So on the other hand, there are other methods which are passive methods, which are data free, and they measure importance of filters without involving any data set. This is where I do work in passive space, because computationally it's less demanding and it's faster as well while computing the importance of filters. So some of the heuristics or the criterias that are being explored for this passive importance calculation of filter is the similarity based, where we first do tensor decomposition of filters from a given layer, and then you measure the similarity among filters in the representative space, and based on this redundancy analysis one can come up with a set of filters which are informative and which are redundant. So redundant filters can be removed from the whole network. Or other methods such as the norm based method, where the assumption is that the low norm filters, low norm means the L1 norm filter, just take the absolute sum of coefficients. So low norm filters numerically they have least effect on performance, so one can remove those filters. So this can be one of the criterias. Or the recent one that we have explored is the significance based, where we analyze the geometry of the filters, how well they contribute to in producing the output. So a filter producing significant output means that it captures the significant features from the last layer, and should be retained to capture most of the information learned by the network. So this is where the significance based criteria also can be chosen. And some of the other methods are exploring graph based centrality measure, where one can project the filters on the graph nodes and then measure the centrality, which will be the indicative of the redundancy within the network, how one node within a graph can be replaced by the other nodes. So once we have identified the criteria, the rank the filters based on their importance, based on any of these criteria, then the next step is to obtain a prune network by removing those filters. And then we analyze the performance of the network, and generally we find that there's a reduction in the performance, which is a bit better than the random performance given by the same scale architecture. So to overcome or to regain most of the performance, one can do lightweight fine tuning, which involve 20 to 30% efforts as used during the training of the original model, right? So we start with taking an unpruned network. Here I showed set of unpruned network from A, B, C to E. So let's take this network, which is existing network on the GitHub. So it has this much performance, and it is used to classify different set of audio events in the surrounding. More than 500 events it can classify. So it has set of parameter count and MAC operations. So we use this network as a baseline or unpruned network. Then the next step is to once we have chosen this pre-trained network, let's compute this filter importance. So let's assume that we have used the significance based criteria, and once we have identified the ranking of the filters, so then we, based on the user defined pruning ratio, which means that the number of filters that we want to remove, So that solely depend on the requirement of compression, how much you want to achieve. So if the hardware requirement is very high, so you set up this pruning ratio pretty higher. Otherwise, you can 50% pruning ratio is more or less sufficient to regain the similar performance. And then once we obtain the prune network, then lightweight fine tuning is performed. So here this plot shows the performance versus iteration during fine tuning. So the baseline performance was this much, and here red line shows that when we prune 25% of the filter from the network. So we see that let me mention that the pre-trained network that we choose is trained for 600k iterations. So once we obtain the prune network, then it can retain the similar performance with only 20% of the original efforts that are used for pre-training of the original network. So we can retain the similar performance, and as we remove more filters from the network, as shown with the green color here, so we can obtain similar performance but with slightly more fine-tuning efforts, right? And removing filters from the network, we can save the memory from 300 MB to less than 100 MB, and also we can reduce the multiple accumulated operations as well, while improving the performance because of involving this fine-tuning at the end, right? So we start with this 100% parameters, then we remove 25% filters, obtain this much performance better than the baseline, and then with more reduction in filters, we can still maintain the performance. But the moment you move more pruning, more filters, then there is a point where the accuracy or performance reduces below the baseline performance. So still we can achieve by reducing 75% parameters the same performance. So that is the trade-off or the line that we need to stop the pruning things. Okay. So the question that is how to choose which layer to prune from the network. So one answer is first, since we have the access to pre-trained network, let's analyze this architecture. So here on the left, I have shown the PANS network unpruned model. So let's analyze this architecture, and we find that most of the parameters, 99% of the parameters, they lie within the last few layers, right? So we tend to remove the parameters from those layers only. And other criteria might be, that's very tedious one, so you can do sensitivity analysis of each layers, and it will involve combination permutations of different layers, but that again consume more time. So best, I think, that we observe is that, so you observe the architecture and come up with the architecture plan where the computations are high, where are the parameters within the layers are significantly higher. So if we compare the passive method that doesn't involve any data set with the active method which uses data set, so we find that the performance wise we can still achieve similar performance, but without involving any data set. The advantage is it takes less pruning time, means it's the computation time to tell the importance of filters within the architecture. And also with passive method, you do not require much filter storage, feature map storage as well. So it's almost 10 times lesser than the active method, still achieving the similar performance, right? And this comparison is done at similar reduction of parameters and MAC operations. Okay. So finally, the inference latency wise, to see how this pruned model is advantageous compared to the unpruned model when we run on the hardware for inference. So for that, we use different set of hardwares, GPU, CPU, and Raspberry Pi across different models. So the observation is that the pruned model which maintains similar performance to the unpruned model can achieve better inference latency, or make latency things faster during inference for CPU and Raspberry Pi system. And on GPUs there is a saving in latency, but the significantly, if we compare with the Raspberry Pi and GPU thing, Raspberry Pi and CPU thing, that's not that significant. And this is pretty clear because GPU has its own power and powerful hardware to improve this inference time. on its own. But from the edge computing wise, running system on CPU and standalone device, pruning is really beneficial. Right? So other methods that have been explored in the literature are knowledge distillation, quantization, and neural architecture search. So this pruning method also can embed into these methods, like for example, the quantization. So you can prune the model, then do quantization as the last step to reduce the memory footprint further, or in the knowledge distillation step. So you can do fine tuning with knowledge distillation rather than training the prune model independently, right, for better performance. So in summary, I would say the AI deep learning models, they are pretty very well and performing state of the art. But the other side of AI is also crucial, which is resource hungry and energy memory inefficiency of AI models. And particularly this is important for edge AI and on-device computing, where compression can help to reduce the computation and memory footprints. Pruning is one of the ways with passive approach to get smaller models. And one of the takeaway that I would say to the audience is the take a pre-trained network. If you find any existing large scale network and you want to deploy for your downstream application, so take a pre-trained network and prune it passively, and do light fine tuning with the base model dataset or the downstream dataset that you have, and then use for downstream task rather than training the whole system pruned kind of architecture from scratch. So further steps that we are exploring, this is with Eric and his team as co-lead with data efficiency side. So we would like to improve the sustainability perspective of AI from the data perspective as well. And the idea is to look holistically to make AI more sustainable from development cycle to deployment cycle. Right. With this, I would stop here, and these are some of the publications, contributions that we did within this passive pruning space at CVSSP University of Surrey. So thank you very much. If you have any questions, please feel free to ask.